And so our first speaker is John Protzko. Is that how you say your last name?
Protzko.
Protzko, and it's a new announcement of a new initiative. I'll let you start.
Thank you very much. Oh, I can't share my screen.
Now you should be able to.
Perfect. There we go. All right. All right. Thank you. So this is more of like a coming out party for what we hope will now be a new initiative at the PSA. So I'm John Protzko. I'm one of the associate directors here at the PSA, and I call this PSARP, or the PSA Rare Populations. So it's just going to be a very short little introduction to what we're planning on doing moving forward. So, and I'm actually glad that Miguel is here because I steal a phrase from him, but I do cite you, Miguel. So not fully stolen. So rare populations have helped us leap ahead in psychology research, and things like split brain patients, right? Mike Gazzaniga's split brain patients gave us the idea of the interpreter and taught us deep things about cognitive science. Trauma, people who've experienced trauma have taught us a lot about not just the process of trauma and healing, but also about resilience. Geniuses, savants have changed the way that we think about the human mind. It's really expanded our limits into what human beings can become. But two of the big things here is, first, members of rare populations are not free from cultural forces. And that's something that gets forgotten is, the people with a certain ability or a certain diagnosis, they are people and they are affected by their cultures as well. And so when we do research on the rare populations, we have this confluence of what makes them rare and interesting, and also the culture that they come from. But also is the trouble is that the N in these studies is by definition small. You cannot be simultaneously a rare population and common. Right? Gazzaniga's split brain work was on 8 patients entirely. Right? We have very low numbers. People with certain beliefs, or people who are in the top or bottom percentiles of certain traits, are by definition rare. And therefore, doing research on these populations, though incredibly theoretically interesting, ends up being very difficult to draw meaningful conclusions from, because we have exceedingly low power, which is tough to deal with. So the PSA, as of this morning, I think we're dealing with 1,254 members in 82 countries. And this is our map. And that's huge. Like we sometimes forget just how large that actually is. And for example, PSA06, the University of Moral Decision Making, is a project that I was the project manager on. And in that study, we had 45 labs, and we recruited 41,090 subjects. Like, that's an absurdly large number of people. And it's wonderful to see done. So what I'm hoping to do with the PSARP, the PSA Rare Populations, is to leverage the ability of the PSA to find people from rare populations and contribute generalizable research that is very theoretically motivating. So we have the opportunity to conduct psychological research on rare populations at an unprecedented scale, provided that we can find the people that meet the criteria for these rare populations. Every lab can conduct it and find 2, 3, 4 of them. And that's about as much as a single lab can hope to do. But with 100 labs, all of a sudden we have theoretical advances that have not been seen in psychology. We get to expand the PSA's epistemic diversity. This is what I'm stealing from Miguel Salon here, right? This idea of a lot of the PSA started with social psychology and cognitive psychologists, but people who do work in rare populations also come from other fields. And we can expand our membership to these fields as well. And we can continue our mission of creating generalizable knowledge, which after all is the home mission of the PSA. Because people in rare populations are also subject to culture, we can start to tease these things apart in studies like this. So what are the next steps? The next steps in this is to create a call for proposals. Right. This call for proposals, we're going to collaborate with community building here. And we're going to reach out to experimenters and psychologists and researchers from all sorts of fields, right? Cognitive science, perception, neuropsychology, trauma, abnormal psychology. There are potentially no limits to who we can reach out to. People who do work in rare populations or have the ability or the theoretical expertise to work with rare populations. Right? They will submit proposals. These proposals will be judged on feasibility and ability to draw theoretical conclusions, regardless of the direction of effect. That might mean this research is descriptive or qualitative or mixed methods. But that's going to be one of the major things that that is part of this proposal system. We will not just be relying on statistical significance. The proposals will be judged not just on feasibility, but will this make a theoretical contribution regardless of how the results come out? And that burden is on the proposers to figure out how to do that. And we're going to collaborate with study selection. Kathleen Schmidt, who's the current chair of the study selection committee, has agreed to help with this process. Right. But, and I stress this a lot, we are going to approach this cautiously, right? We may not select a study that comes in, right? It's better to do this right than to just do it. Out of the studies that get proposed, none might meet our criteria. They may be too infeasible. They may only rely on a subset of the PSA, which we don't want. We want to look at people who can represent us globally, or the theoretical contributions might be too dependent on a direction of effect. Right? If nothing is strong enough, we will not accept anything. We will regroup and we will try again. Because that's the goal. The goal is to do this right. As part of this, the proposers have to give step-by-step instructions for screening and locating members of the rare population. It's not going to fall to us, the members, to find these people. We are going to be given, as part of the proposal system, step-by-step instructions that will go through feasibility and help us find these people. That can involve screening subject pools, collaborating with people at institutions in other fields, selective recruitment, how we find participants. But again, this goes on the proposers. So this is the PSA Rare Populations Initiative, right? We are one of the largest research consortia in the world, which is wild. We span the globe and we can find people. We can find people from these rare populations and we can test them. Thank you.
Thank you very much. Is there any questions?
Yeah, I have a question. That was a great presentation, John, and I think it's a interesting initiative. However, one question that I have is, how do you define rare population? Do you mean, for example, racial minorities in a society, or, for example, I don't know, people with mental disorders? What is the criteria for defining rare population?
It's a good question. I'm not planning on providing too much criteria ahead of time. I'm leaving this on the proposers, right? So if a study wants to use people from a minority group, that might be a rare population, but that doesn't necessarily correspond to a global consortia like we are, unless that minority group can be found all over, or maybe the minority group is indigenous people, regardless of what country they are indigenous to, right? But that's on the proposers. If they want to do people with a diagnosis, if they want to do people from minority groups, people who've experienced something, people with a certain ability or who are very high or very low on some trait, that's on them.
Mm-hmm.
Great. Any other questions? Thank you, John. So if not, then we'll move on to the second talk by Peter. Oh, sorry, did you want to say something, John?
No, just thank you.
Oh, okay, thank you. The second talk is by Peter Mallik, and it is on assessing the generalizability of visuospatial bootstrapping to novel stimulus type.
Thank you. I think you're going to have to remake me a co-host again. So I gave you full host powers when we shifted, so I won't be able to share my screen. There we go. All right, thank you. So before I do that, it's a tough talk to follow. John did a really good job and really cool initiative. So kudos. Talking about some really large scale stuff, and now I'm going to go take it, funnel it back down and talk about some really small scale stuff with relatively small n. So all the things that we hate, but doing research in a pandemic was kind of the context of this. So this is kind of where we're going. So let me get my PowerPoint up here. All right. Ooh, started too late. There we go. And all right. Hopefully everybody can see my PowerPoint. Okay. So just for a little bit of context, I run a research lab in Ashland, Ohio, where it's kind of the middle of nowhere, very small town, relatively small campus. And the pandemic definitely hit us hard from an in-person research perspective, just like it did everybody. So in the midst of that, as we were returning to campus in the autumn of 2020, we are thinking as a lab, what are some kind of things that we can be running and testing and collecting data on in the meantime, since some of our more recent research initiatives have really been put off. We're primarily a cognitive aging lab, and studying older adults is something that was taken away from us during the pandemic, and who knows when that's going to be fully back, at least locally for us. So we really wanted to do some studies, conduct some original research, just for student participation, as well as trying to just come up with some really small contributions that we could. So the inspiration for this particular study came from a few years back when I was reading an article on this specific topic, which is visuospatial bootstrapping, which we'll go into in a moment. Way back when I was a grad student, I was like, oh, this would be a really cool thing to do a study on, to see how this generalizes. And somewhere in the back of my mind, that rested for about 4 or 5 years. And then this fall, I'm like, oh my gosh, my time. We needed something to do. I'm like, this is what I wanted to do all those years ago. We're going to do it. So just before we dive into that particular topic, I want to do a little bit of rundown on just running some cognitive replications, right? Especially in small labs around the country. We have different array of resources, and just wanted to make note that this kind of research is definitely possible on a very, very low budget, which is what we managed to accomplish. So it's important to try and run these kind of things. So we wanted to test some established models, which is why we picked this particular one. So kind of in line with the broader scope of the PSA, what are some of these generalizability and replication standards for some of these well-established cognitive models? So the one that we were really interested in, and kind of where the visuospatial bootstrapping effects stem from, in terms of their inspiration, they stem from the Baddeley revised working memory model. So I don't know how familiar folks are with that, but I'll just kind of give it a little bit of a rundown, not too in depth, just to keep this kind of surface level. So essentially, if we think of working memory as a cognitive system that allows for the storage and manipulation of information in order to complete a task, this model tries to highlight the different subcomponents of working memory. So we usually don't treat working memory as one product, but as a combination of different functions that are kind of aligning to result in the process. So it's broken down into different subcomponents. So the Baddeley model and the revised model that we're looking at. And those components are the phonological loop, the visuospatial sketchpad, the central executive component, and the episodic buffer. Those are the ones that people who've taken cognitive psych classes have been bombarded with for probably, the revised model came out in, I think, 2000. So 21 years of bombardment on these topics. So we really wanted to see if this model generalized, or test a specific topic related to this model. So the revised model added the episodic buffer subsystem, and that was subsequently tested by a research group starting off in about 2009, if I recall correctly, using a method called visuospatial bootstrapping, which is something that I am in a way a full expert on. but it's something that I really wanted to explore, which is kind of cool. So that's another neat thing about replication studies. You can kind of really get into these different topic areas as much as you like without having to fully embrace the literature, even though that's what we're trying to do. I was just out of curiosity, go on and explore this. So let's introduce this topic now. So Stephen Darling and colleagues kind of came up with this bootstrapping idea. So visuospatial bootstrapping, just as a general rundown, is if you can present verbal working memory in a way that has a visuospatial connotation, you see a boost in working memory performance. So if you do like some sort of serial recall task or something like that with a sequence of numbers, if you present the stimuli in a way that has a visuospatial array that's encoded within long-term memory, you see a boost in performance. That's the bootstrapping effect. So this was done several times with a few different iterations of stimuli. So the one that was used was a typical keypad display, or TKP, or if you're my co-authors, you're constantly correcting TPK because of my mild dyslexia. I'm pretty sure there's some of those that I might have flipped around in here somewhere. I always mess those up. But these original studies did a couple different variations of the keypads. These are typical keypad with which I'll have a picture on in a moment. But they also did some variations using novel keypads. So if you have a typical 9, or well, technically 10 digits with the 0 in a keypad, but you mix around the numbers, that wasn't effective. So the typical keypad was effective, which indicates that, or provides evidence for that previously established or encoded visuospatial arrays that are condensed can result in a bootstrapping effect. So that was the general consensus from these papers. And we found that pretty interesting. So kind of with the PSA hat on a little bit, it's like, okay, so how does this generalize? So if it's true with keypads, it must be true with other well-encoded visuospatial images or arrays. So what we wanted to do is see if it generalized to an analog clock face. So an analog clock face shares a lot of similarities with a typical keypad in terms of the size, the condensed shape of it, as well as the technical number of units. So while you might think of a keypad as having 10 spaces, there's also the spots at the bottom for the pound sign and the asterisk key. So it does have 12 spaces like a face. So that's kind of what we set to do. So our overall entire goal of this was, does this bootstrapping effect generalize to other well-encoded stimuli, and do the typical keypad findings replicate? So let's do a little bit of a methodology rundown here. So with a relatively small sample size, given the constraints of the pandemic, even though this was relatively okay power-wise, considering most of this was entirely within subjects, repeated measures, we managed to get 63 undergraduates in just a span of a few months when we were able to do data collection. So I was pretty proud of that. And we did a working memory probe task. So we didn't do a full replication here. We did a more of a conceptual replication. And I'll run through a trial example in a moment. It's not going to be perfect on PowerPoint because we use ePrime, but essentially we'd present a numerical sequence using either a single digit, the clock face that you can see on the bottom left, or a variation of that typical keypad on the bottom right. That image is a little bit quirky because it's saved as a JPEG and things get moved around a little bit, but it was presented in one of those three states across different blocks. And we did a probe task. So we present a number in a sequence across different working memory loads. And then the probe would say, recall a specific number from that sequence. So you have to hold the sequence within memory and then recall a specific unit from that sequence. Loads variations were 5, 6, 7, 8. So they're getting progressively more difficult. And we had 20 trials within each block, which were counterbalanced based upon load and based upon which position was being probed, essentially. So we did find some quirky stuff, as you tend to do when you have relatively small sample sizes. Some of the stuff that we found worked pretty well, some of it didn't. So before we did that, I want to give you guys a little bit of an experience of what a typical trial would look like. I don't know quite how this is going to come across in a Zoom-based platform, but bear with. So I'm going to have to go through the button pushes one by one. It doesn't have the same temporal precision as E prime, but bear with me. So I'm going to present a sequences of clock faces with pointing to specific numbers. And at the end, it's going to ask you to recall a specific number from that sequence. So I'd like you guys to get a pen if you have one or something to write with. When I present this sequence, don't write the sequence down. That's cheating, as I would tell my students in the lab. I told my RAs to tell people that. And then I'll have the probe question come up. This is a PowerPoint variation of what was E prime. In E prime, they'd be typing in the actual number they saw, but this is the best what we've got combining these kind of tools. So I'll start in 3 seconds. So 3, 2, 1. So then the probe question would come up. So what was the fourth number presented? And you can write that down. I know that wasn't a perfect representation because I had to manually push through those slides. So I'm not quite how sure my drumming rhythm is. So does anyone have that number handy? Go for it, John. 9, yes, correct. It was 9. Good. So it's a little bit easier than having to do an entire recall of a sequence, which we recognized. But we wanted to try a slight variation in terms of a conceptual replication rather than an entire full replication in that. So try and do things a little bit differently. So what did we end up finding? Okay, so we found, as I mentioned before, a couple little quirky things, but some things that we expected. So I tried to condense the results. I didn't have space for everything. We did all the different plan comparisons and things like that across everything. That wasn't included in this slide, but if you're curious about that, I can share those with you, I suppose. So as we kind of expected, we did see significant effects for the stimulus type, aka if it was presented in a single condition, so a number by itself without a visuospatial array, in a typical keypad, which was what the original authors used, or as a clock, which was the main novel component here. And we found that main effect was pretty consistent. So in terms of the visuospatial arrays performing better when you collapse across all the loads than the single condition. However, those two went down in a relatively linear fashion, which was pretty interesting. Especially when you look at the clock. The clock was almost perfectly linear, which we found really, really surprising. We thought it would be, we'd see a little bit more randomness there, whereas the typical keypad showed a similar pattern. The single condition was where things got kind of quirky. So we found this funky interaction, this load by stimulus type interaction, which wasn't something we necessarily predicted. We weren't too sure about. And a lot of that was coming from the pattern of this single display condition. So it was kind of quirky. So it for no reason performed worse in the lowest load, which should have been the easiest across all conditions. Then it increased for load 6, decreased again for 7, and then was technically the best in the hardest condition, which was 8, even though you're kind of approaching 4 effect there. So that's kind of what we think was happening. Unfortunately, as things go with science, you can't just go with that kind of logic. You have to, we have to prove things. So that's kind of where we're stemming now. So let's talk about some of the general discussion, and then we'll get into what we're doing now. So I know when I wrote this abstract up, it was a little bit abrupt because we just started working on a second experiment. So it was like very much in that proposal stage when we were doing the design when we were writing this up. So we didn't want to stop here just with this. We wanted to run a second experiment to provide a bit more proof of what we were seeing, at least in terms of the utility of this clock face design, as well as the keypad, and try and sort out that crazy thing with the single condition. So those are the kind of things that we wanted to figure out. So essentially results show here that one, it does appear that the clock face is a valid tool, though it didn't perform as well as the keypad, that we don't really know why that is. So I don't know what's so special about a keypad that other different arrays wouldn't work as well. That's something we need to really try and dive into and explore and try and replicate that difference is this. That was one of the things that we didn't expect. We thought they would perform equally well considering they're both encoded visual arrays. So the clock face was better than single, which says there is at least a partial bootstrapping effect there, at least from our small sample. Again, should be replicated. But we need to get around some of those funky things. So the next experiment that we wanted to do was more of a direct replication using that full sequence. So one of the things that we suspected is because we used a probe-based task, it is inherently easier than a full serial recall task. So that might have been some of the reasons that we saw some of the patterns we did. So doing a full replication in the second experiment, having the same stimulus loads and then having different visuospatial arrays like we did, we wanted to see if those findings were consistent in a much more difficult kind of setting. So additionally to that, we added a mixed condition, which was a mix of the clock and the keypad, so combining visuospatial arrays. So we wanted to see and kind of explore what type of combinations could be involved here. So it's kind of very much a basic science kind of understanding of visuospatial bootstrapping, but we want to see how those generalize. So just to kind of finish up here, kind of getting close to time. One of our future directions that we want to explore with bootstrapping is maybe look at some global differences that exist. So what type of arrays will generalize, which ones won't? So keypads and clock faces are pretty universal globally at this point, but what are some maybe more specific localized stimuli that we would expect to see some differences? I think that would be a really cool potential avenue to pursue in the future. So without much further ado, I want to thank my lab specifically. Going through this in a pandemic was one of the most difficult things for these students. They're in research lab for a short period of time as undergraduates, and they just had such a good attitude. So thank you to all of them listed here, as well as my colleagues. So I'll take any questions you guys have in the last couple minutes of my time. And I thank you all for hearing my spiel.
Thank you, Peter. Is there any questions?
I guess I have one. How fast was, I might have missed this too, I'm on much cough medicine. How fast was the RSVP part of that? I'm assuming it's kind of like an RSVP task, yeah.
So in terms of the presentation, you mean?
Yeah.
Off the top of my head, I believe it was 500 milliseconds in E prime, but I could be wrong. I think that's what it was. So
long enough they could see them, but to prevent rehearsal.
Yeah, so 500 milliseconds for the numbers. I think the masks were 250 milliseconds. I'm not quite sure.
Makes sense, because I was in there like, man, this is easy, but then you're like, I'm clicking through this in PowerPoint. I was like, all right. So it's much faster on the screen normally.
Yeah, I was trying to click through it. It wasn't like pushing buttons.
Is there any other questions? If not, then and I think Peter freezed. I hope that's all. we got everything that he to say. So let's move on to our last talk. We're right on time, so that's perfect. And we have Erin Buchanan, am I saying that right? Here, and she'll give us a PSA big team update.
Now you can hear me? Yeah? And people should be able to see my screen. Okay, cool. I'm gonna click on the chat. I thought I could see both at once. I can, thank you. All right, so thanks to both of you before me. I actually was double booked and presented briefly in the other room, but I have heard Protzko's spiel and I'm sure it was great. But I will give you now an update to 007. Which is the SPAML. A lot of the names I recognize in here, so you're going to get the update early, because otherwise you'll hear this tomorrow. And I've jokingly called this cross-linguistic research is hard, because it is. This is also a mini preview of the psychonomics talk I'm doing next Sunday. I've never had to go on Sunday, but this is my year apparently, is to go on the last day in the session that no one wants. So hopefully you guys will be more receptive than they will. So let me give you a quick outline of what I'm gonna go over today, and I'll try to leave some question time at the end. I'll give you a very quick overview of the actual SPAML project if you aren't familiar or have forgotten, a specific description of why this is difficult and the key issues that I have been thinking about, where this project and the other related projects are at the moment, which is better than it was last month, and then, excuse me, leave room for questions at the end. So a very quick overview. This project is associated with semantic priming. So it stands for semantic priming across many languages. And semantic priming, if you aren't familiar, has a really long and rich history in cognitive psychology. As pretty much as soon as we figured out that people do this, we've spent a lot of time trying to figure it out, with many other variables interacting. But basically the idea is that it occurs when a response latency, so how long it takes you to respond to something or read, those response latencies are facilitated, meaning they go faster. So it improves our cognitive skills when word pairs or objects are related versus unrelated. Okay? So if you see dog, cat, you're gonna be much faster cat than if you saw dog, spoon. Although I've used dog, spoon as an example so many times at this point, I probably would be pretty quick at dog, spoon. And so that relatedness between dog and cat, we think speeds up cat. There's a lot of ideas on why semantic priming happens, but what we're focused on in this study is just sort of the reliability and if it even is real, which you think at this point cognitive psychology would have figured out, but there's a lot of questions over sort of the stability of semantic priming. Is it only certain items that give you this effect? Is it universal? And then the many languages part, is it consistent across languages? That's usually measured with what's either called a lexical decision or a naming task. In a lexical decision task, you're simply asked, is this thing a word or not? And so the participant in the study is just answering on a keyboard, yes word, no not word. Or naming, where you read the words aloud. This also allows you to study people's reactions to non-words. Not interested in that, but it will be data that we are collecting for others to investigate. And it's based on the work from the Semantic Priming Project, which is, gosh, oh my God, almost 10 years old at this point, that provided priming values for a seemingly very odd number of English word pairs. Please note that this is only in English. And while I was involved with that project, there are some key limitations to it that allow us room to improve. You can see a demonstration. I think this should work. Yeah, of the study. We're programming this with Felix Henniger's Lab.js to get accurate response latencies. Right, millisecond timing is really important on the web. There is a history of doing this work on the web. There's a previous study called SPALEX, that's Spanish lexical decision times, that got some really good results. So I saw somebody else commenting about web research. we're hoping that this also runs as well as SpotLex did. Okay. So we have participants tell us a little bit about themselves. These are sort of the standard questions about that people like to know that don't get us in too much trouble with GDPR and don't allow people to remain anonymous. So I'm just going to pick some random answers here. This at some point will actually take you to different versions of the experiment. It does not at the moment. So what we show people is like, hey, you're going to see some words. Tell us if you think it's a word or not a word. And I have to remember what the options are here. So S for real word, L for fake word. Okay. Now they stay on the screen as long as the person is, and at some point it'll time out. Well, they see this set of options here where they get feedback. Oh, that was not right. Oh, it actually did give it to me in Dutch. I think my programmer has beat me to it. I was like, why does that say it's a fake word? Okay, I don't know Dutch, so this is gonna be a fun experiment today. All right. These are in English. So then they would go on to the real task. Sorry, that was kind of amusing. And you would just do this for as many trials as we're gonna give them. So we're trying to keep this to about 30 minutes. And pair it with some other tasks that we're interested in. So let me see if I can go back to my presentation now. Yep. So that's what a lexical decision task looks like. It is very fast. Participants just like bang through this stuff, like yes, no, yes, no, yes, no. Where the excuse me, average response latency varies from like 500 milliseconds, so a half a second, to like a second and a half if the words are really weird. All right. Now, the part to me that gets difficult is when we start to expand this into other languages. So there's clearly a data set for English. Are there other data sets? Yeah, in other people's labs, but are there other big published data sets? Not really. Okay. Are there other data sets in other languages? Really, not really. So one problem that we see is that once we start to like try to combine data sets across all these very large different options. So I'm just talking about priming tasks right now. There are data sets for, I see Maria's here. So, semantic feature production norms, which is just what makes a zebra, right? Stripes. There are data sets for other cognitive variables like age of acquisition. How old were you when you learned this word? How concrete is this word? Like there's a huge number of these things. So let's start to try to put those together. Maybe we can predict priming from all these things. And then that's when you start to see the problem, right? Where the increase in publication rates, which is this pretty graph over here from a paper, ignore the last bar because at the time that we published this last year was not finished, but you can see that there's an increasing trend in publishing these data sets for others to use, and especially kind of with the open science uptake. But once you start to combine them, that multilinguistic, meaning multiple languages, overlap is still pretty poor. So it becomes hard to do this kind of research. So the goals of this project are to help. So we're going to create an online framework for data collection. You've already seen a little preview of it. And that's really modeled after the success of the Small World of Words by Simon Dedenne. And they still have their task up and online. So if you ever want to just like tell people what you think about words, if you Google Small World of Words, you can do it in about 15 different languages. If you don't know Dutch, I wouldn't recommend Dutch though, unlike what I just did. Create this large multilinguistic priming data set paired with some other cognitive variables we're interested in, like concreteness, age of acquisition, and then provide a package modeled after Jack Taylor's really great LexOps to allow people to interact with this data because it will be quite large when we're done. And I fully expect this to take waves of data. So what the Small World of Words folks did is as soon as a language was done, they published it. And so for the PSA version of this project, we'll have a couple of languages that will agree to publish, but then after that, keep collecting data through grants or through other interested researchers and publish this in waves. So I expect this to be more than one publication because the nature of these data collections, it would be lovely to say, here's 55 languages of priming, but I just don't think we'll get to that kind of data set in a reasonable time. So we're going to kind of stop and publish as we go. Unless somebody just has tons of money, and then I will happily take that money and we'll publish all of it at once. Okay. If you're interested, I think most folks in here are already on this project, but you can email the team, and that email has been being ignored while I was on vacation. So you'll get emails back starting tomorrow with updates. Okay. Now back to our problem here. So how do you create stimuli for such a for a study? Okay. What people used to do was they would just pick the words that worked in pilot studies and then keep using them, which was maybe part of the problem. And so we can take these data sets that we have and calculate their similarity. And I want to say this slide is all Maria, because she's the one who was like, you really should be better at defining this. So similarity is the shared meaning between concepts, right? So how much are dog and cat similar? Well, they're both pets, they're both small animals, they both have fur, right? But defining similarity can be face value, right? So dog cat just seems more related than dog spoon. And that's how a lot of the early studies work. Okay. These words work, so let's keep using them. It could be the number of shared features using what we call feature production norms, right? So how many times do they have the same listed features by participants? If I ask you what makes a dog, people make a bunch of a list of words. How many times does that same set of words come up for cat? Okay. We could use association strength from the free association norm. So what's the first thing you think of when you hear dog? A lot of people say cat. Okay, barks is another big one. And that's what the small world of words did. Or we could use co-occurrence from computation models. And this is what we actually did. So using very large data sets of text, we can build these models. I've always called them vector space models. Other people call them different things, but these network and computational models that tell us how related words are because they appear in the same texts or the same types of texts. Or and so it's a famous quote, words that are similar, like I've lost the first quote now. My brain today, you guys. Words that occur together are similar, basically, is the idea. It's kind of modeled after that Hebbian quote of neurons that fire together, wire together. Words that appear in the same text or in the same types of text are very similar. And the cool thing about picking text corpora is that you don't have to ask participants to do anything, which means you don't have to deal with how participants can be. And so where can we get this corpora? Well, thankfully, the Open Subtitles project is freely available. It provides linguistic data, just really large data sets of movie subtitles in 50 plus languages. I think it's actually almost 60, but not all of those are usable. And you'll see why in a second. And that link there is live. You can download the data sets. They're quite large, which is one reason why this took so long to get this part of the study done, is that, you know, computational power is limited sometimes. And why subtitles? Well, subtitle research has shown that the word frequency, which is the answer to everything. When I teach cognition, I tell my students, if you don't know the answer, write down word frequency, because about half the time you'll be right. It predicts half of everything in cognition. Is really good from subtitle data, right? Because that's how people actually talk, versus using big text corpora like Wikipedia, right? So we're modeling our language models basically out of what people actually talk about. And that has been really quite well supported in the literature to predict response latencies and all kinds of other stuff. So we're going to go with what we know, and we have big data sets. Okay. And then I know Gary Lupian has been doing a bunch of work with these. So if you really want some very cool pictures, especially gender stuff, you can look up his research using these exact data sets, and he's got some really cool graphs of how different people talk in the movies and that kind of stuff. And so from there, what we've decided is we're going to use nouns, verbs, adjectives, and adverbs. Okay, these are the meaning-making words in a sentence. They're the ones that work well for priming, like the word for doesn't do a whole lot for people in priming, or the. So we're going to focus on those words. Okay. So I got to know what's a noun and an adjective. So I need a part of speech tagger to pull those words out. Okay. And this is where the UDPipe package comes in handy. I discovered this recently. It's really one of the most fantastic free part of speech taggers. It runs in R. They're like a couple comparable ones in Python, but this one definitely has the most languages. And it's an open source project to provide new languages. So they're constantly adding things. And it will tag sentences for you. So I just gave you a little example. It provides more information than just the part of speech, but I'm only showing you that here. So it actually also does lemmas, lemmatization, which is really handy, and dependency parsing, if you're interested in that. Okay. So from here, now I can just say, okay, the only word out of this sentence that I would use is package and great. Then each one of these language corpus sets was analyzed to see if there was a corresponding UDPipe model. So this took us down to about 44 languages. It was actually 45 for a while until I realized that we didn't have Brazilian Portuguese and that it probably was going to match regular Portuguese. I know they're not really the same, but the types of nouns and adjectives that people use are the same. So we have 44 languages that have a UDPipe model and an open subtitles model. And for 4 of those languages, we also added in the Wikipedia corpus because we didn't want to lose them because they're diverse languages, but their data sets were not quite large enough to say that these were the words we wanted. So for that, it's Afrikaans, Hindi, Armenian, Tamil, and Urdu. That's 5, sorry, languages. We added the Wikipedia corpus to get a good model to help us pick the words. We took out all the stop words, the, and, a of the kind of filler words in a sentence, all the actual numbers, like the literal number 3, not spelled out word numbers, like the word 3. Okay. Anything less than 3 characters, which is usually covered by stop words. I will note that that didn't apply to things like Korean and Chinese. The Chinese is a mix, it's both Mandarin. I have both Mandarin and Cantonese, but obviously character means something different there, so that's not true there. And then everything's filtered down into nouns, adjectives, and adverbs, as best we can tell. Because obviously once you start translating these between languages, you get kind of phrases sometimes, but based on the part of speech tagger, those are the ones we grabbed. Then pulling their word frequency, we took the top 10,000 words from that piece. Okay. So we're trying to really grab really frequent words because then we run less into the problem of these like weird words. So one problem with the semantic priming project is they do have some weird ones in there, like McDonald. So trying to avoid that, but also words across languages. So I say it's a weird word because that's not going to be a priming word in another country, right? In the same way that it would be in the US. And so words do act differently in different areas of the world. So a funny story is we used to use the word hero, like superhero, and sandwich together. And in some parts of the world, that's a really large sandwich. And in other parts of the world, it's not. And so I moved to universities and it stopped working. So we had to ditch this set. So this is not just a cross-language problem, it's a like within language dialect problem as well. So let's take those really frequent ones because hopefully those are somewhat consistent. Right. And that's 44 different languages, which I'm really excited about. From there, I calculated similarity by using a fast text model based on the subtitles or Wikipedia. And we didn't actually build these models. We stole them from this recent project by Van Peerdon and Thompson. Another one of our pre-projects is actually dealing with some of the issues with that project, but we're using it because it should mostly consistently work for us. And calculated the cosine between words for each of these. that if you're interested in what a fast text model is, it's a vector space model. So it's kind of like it is Word2Vec. It's Facebook's version of Word2Vec. Or if you're familiar with LSA, these kind of models that build dimensions by words. And so it's got 300 dimensions. If you have no idea what any of that means, kind of think about factor analysis. Right? So it's not documents or anymore. It's kind of a representation of the themes in the text. Okay, with a 5 window count size, which nicely maps onto how much people can read at once. Okay. And a different project is looking at like, do all languages map onto 300 dimensions? I don't think so, but this is what we're using for this project. Okay. So we're pulling out cosine. Cosine is a measure of vector similarity. It's really similar to correlation, but it's a distance measure. So it's bounded from 0 to 1. So 0, no relationship, never occur in the same types of text, no themes in common. 1, they always occur together. They are always in the same types of documents and the same themes. 1 would be really hard to get unless it's this exact same word. Okay. And from each of those 10,000 words, we pulled the top 5 cosines because I want like nice, strong related words that we can use. Okay. And top 5, and we're talking about cosines that range from like 0.5 to 0.7 for those familiar with this work. Now, here's the somewhat tricky part. How do we make sure the words are all the same in every language? Right? Because the whole point is to be able to compare them. So I did convert them all back into English because that's the language I speak. That is a limitation here. And merged all that into this like giant data set that is literally like 1 million lines long and like 700 columns wide to grab all of their word pairs, right? And so, okay, like I said, it creates 1.2 million pairs because some pairs are in some data sets and not others. And the average overlap across data sets is only 3%. Oh, this is where it becomes hard. This is why cross-linguistic research is hard. And so it ranges from 2%, the word pairs are in 2% of those 44 data sets, to 70%. Now 70% are moderately predictable, off, on, brother, sister, very good, bad. Okay, these kind of very common antonyms, okay? Or brother, sister are more synonyms. So we sorted those by their language overlap. Let's use the ones that are in the most data sets. And it picked 1,000 pairs. This took forever because each word can only be used once. And the words are not different forms or different lemmas of each other, right? Run and running. Okay, that's a different type of priming. I want to focus on semantic priming here and not either phonetic or orthographic priming. And limiting the use of proper names. They are movie subtitles, so you have to avoid the kind of use of names and countries. So some countries are in there, but try not to use every combination of countries as our primers. And then limiting the use of numbers, colors, and days of the week, because those are very popular as well. Okay. Now, the overlap between languages is still difficult. This is the main key point here. The mean overlap is 28% of those 1,000 words. The pairs, they appear in 28% of the data set. So the rest of that will have to be translated, which leaves us about 700 words to translate for each language. And then I just made a graph of, for each word pair, how many languages was it in the top 10,000 words and came up as a pair. And it's kind of nice range. So we can see that already that like priming may be really variable across languages, just simply because some languages don't have these relationships that others do. All right, so some thoughts on the selection, and then I'll give you the kind of project updates. Multilinguistic research is often only in a couple languages at once, like 2, 3, 4, 5. But even with these advances in published data sets, that cross-referencing is still difficult. So when I start to try to put these together, it gets really holy, so to speak. There's a lot of missing data. And one thing I really want to avoid as an English-speaking researcher, a white English-speaking researcher in the US, is leading this as a English and then translated problem. I want the languages themselves to guide me and to tell me what the words should be, rather than simply selecting English words and just direct translating. There's still a little bit of that, but I'm trying to avoid some of the cultural problems that are built into this type of work by not just picking the ones that I know work in English and being like, well, these other languages are weird. So if we can get like a nice mix, we may be able to sort out like priming does work, but it has to be culturally relevant, or there's some different ideas I have on thinking about separating the process from the language, right? So we want this to not be a translation-driven idea, more to be a language-driven idea. All right, a couple more slides. Sorry, I think I'm talking more than I meant to, but a quick set of project updates. If you'd like to join, I have a form. You can send us an email. I'm working on those emails tomorrow. Okay. We're using Canvas to keep everyone up to date. So if you are on this project and you're in Canvas and you haven't gotten a couple of emails lately, you've been missing out. Okay. So we are sending updates going to be more frequently now that I'm back from vacation. And then how do you track what you've done and you need to do? Well, I'm very briefly want to show you. If you are in this project, or if you're not, you can see quickly here. As a student in the class, since this is classroom software, we can't really change the name of that, but what you do is go to grades. Nobody's really being graded here. It's just the grade book's really handy way to track everyone. And you can see, what you've done and keep track of your contributions. So if something here is missing that you know you did, you can send us an email and say, hey, I know I did this thing. Why don't I have a score, so to speak? And you can see that actually I have not, as a student, accepted the collaborator agreement, and I probably should. Right? So that's how you can keep track of your contributions at the moment. The other cool thing is all the announcements. So you can go back if you've been missing them, and you can see that I just sent an announcement like, hey, I've been on vacation, and we'll give you an update later this week. Y'all are getting the preview. Now, a quick update. Everybody just got their first shot at editing the register report. There are 800 plus comments. It makes me a little twitchy, but I'm starting to look through those and working on addressing those. That'll take a couple weeks. Okay. We're going to put together that final draft for everyone to check their information. So your authorship information will be on there if you filled out the authorship survey, and provide us maybe some more, couple small comments, not a big, huge round again, but a short, hey, look at this, make sure that you want your name on it still. Okay. If you missed out, make sure you're getting the notifications and you can join on that second pass of the paper. Okay. We are also, this is brand new, going to apply. ZPED is just put out a call for register report projects. They have access to large panels of people in countries that are hard to get into, like Korea, that I would be really excited about getting that language covered. And their timeline currently works with our goals, which is really exciting. And their support would allow us to cover more languages pretty easily. So things like Russian, Korean, both forms of Chinese, the main two. What else? Romanian. Like that would get us some good options of especially some European languages that the PSA only has a couple people in. Okay. So overall, we have about 150 people on the project, and in an email box I've been ignoring, so it's probably a little bit more than that. About 60 people filled out their information for the register report, and I did a quick view of the languages people are saying that we have so far, and that's looking really nice. Right. So I'm really excited that we've got kind of our coverage of Europe, but we're also getting some languages that have really been ignored in this area, like Arabic. Okay. All right, and we hope that you will want to get involved. Okay. The timeline is to revise the register report. That's ongoing right this moment. I have downloaded it. Every once in a while I open it and Word crashes because it's got so many comments. Send it to the network for final thoughts. Do the ZPED application. That's due really the first week of November, as long as they say, okay, yeah, sure, we like your stuff. And submit that register report to Nature Human Behavior at approximately the same time, because we're hoping that we don't get an immediate desk rejection, fingers crossed, and that they'll kind of push through at the same time. We can update for both of them. They'll give us the panels, NHB will give us an acceptance, and life will be great. Okay. And so we can kind of accomplish both goals for people. What's next? We will have people a need for translators. I don't have a good timeline for you because I have no idea how long NHB will take. ZPED has a schedule. We'll see if they stick to it. So early next year, I'm feeling. Programming, we're working on programming. I apparently didn't know there was Dutch in there, right? And right now, labs can work on their IRBs. So if you have to do a local IRB, all the information is there available for you. Okay? You may have to do a modification once the any changes that happen through ZPED and nature human behavior, but you should be able to get started. Some labs have already done this. And then hopefully Magic will set up the website and get your lab ID going and start collecting data. Okay. Now the data will be born open, so you'll be able to see the data as soon as it's collected. Okay. Other project updates, and then I swear I'm done. We're working on 3 other little mini projects that people can contribute to. First one is Words to Many. I'm working on reviewing the information from that. And I won't go into detail what all of these are doing, but if you have questions, I'm happy to answer. But then we'll have a second round of, hey, here's what we've got. Here's how you can help. This is a PhD project, and the student, I swear, does not actually want to be a doctor some days. So we're working at the speed of snail, but it will get done at some point. Okay. Words to Many is the counter argument to the Van Paradon paper. The subs to Strudel paper, there's still options if you want to help for spell checking. I saw a bunch of people had done work while I was gone. Thank you. I went in and added your contribution. And that one is up next. I've made an outline, so it's coming up. And then the Power to Stimuli paper, which is about building these kinds of data sets and knowing how to properly power them. I have an idea of how people can contribute now, because before it was kind of wishy-washy, and you'll see that come out in the next couple weeks. And I've also started working on the outline for that one. So these are also moving. They don't look like they are, but the things are happening. Soon you'll get an email about it. Okay. All right. Okay, I only went over a couple minutes. My apologies. And so I'd love to answer any questions people have. And I want to say thank you for listening. And all of this code magic is on GitHub.
Wonderful.